Hello, Western. So now I want to talk about what happens when we have a wave that reaches a fixed point. So below I have a little graph here to illustrate this. I have this string here with a wave on it that's traveling towards a fixed point that's anchored to a wall. So when the wave reaches this fixed point, there's tension in the string, and that tension is going to exert a force upwards on this little point. However, because this point is fixed, the wall will exert a sort of normalish-like force downward on this point to cancel the upward force of the tension. Now, if we think about this, the downward force exerted by the wall should create a disturbance all of its own on the string, and that should create a wave that'll move away from the wall. And that's exactly what happens. So when we have a wave that has an initial disturbance that's upwards, when it reaches a fixed point, the wall exerts a force downwards that creates a disturbance downwards, creating a wave that moves away from the wall. So when a wave reaches a fixed point, the wave reflects off that fixed point and gets flipped upside down in the process. So I have a little animated GIF here to sort of illustrate that idea. So here I have this wave that's moving towards the right, and when it reaches this right point here that's fixed, the wave will get flipped upside down and start moving in the opposite direction. Now, in that previous example, I just had a single pulse on a string, but what happens if I have a sinusoidal wave and both ends of the string are fixed? Now, the sinusoidal wave will run into the fixed point and reflect off of it, and as a result, I'll have a sinusoidal wave that's moving to the right and a sinusoidal wave that's moving to the left, and these two waves should interfere with each other. The resulting interference is called a standing wave. So we can understand a standing wave by applying the superposition principle and what we know about how to mathematically represent a wave. So the superposition principle says the resulting displacement is just going to be the sum of the two displacements. And if we think about a sinusoidal wave, remember we can write this as a sine of 2 pi x over lambda minus 2 pi frequency times time. Now this here is a wave that's moving to the right, and I need to add it to a wave that's moving to the left. So that's a sine of 2 pi x over lambda plus 2 pi frequency times time. Now, we can simplify this and rewrite this using a trigonometric identity. So if you remember from trigonometry, sine of A plus sine of B is equal to 2 times sine of A minus B over 2 times cosine of A plus B over 2. Actually, I have that mixed up. It's plus here and a minus here. So now, if I think about what's going to happen here, so A plus B over 2, so if I take this term here and add it to this term, the frequency part's going to cancel because it has opposite signs. So I'm going to wind up with y1 plus y2 is equal to 2a sine of, so I have 2 pi x over lambda plus 2 pi x over lambda divided by 2. So that's just 2 pi x over lambda. I'm going to multiply this by cosine, and now if we think about what's going to happen when I subtract these two things, this term is going to cancel. And what we'd be left with is 2 pi frequency times time. Now you may think I made a mistake here with the sign, but actually this is okay because remember that cosine of minus x is equal to cosine of plus x. So even though there should be a minus sign there, I can just ignore it. So this is the resulting equation we have for the standing wave. Now, there's a very important thing that I need to point out about this that I have kind of illustrated here with these brackets, is that this first term here is the time-dependent term, and it's multiplied by another term that just has the space dependence. So the space and time dependence have been separated. They're just multiplying each other now. Okay? And the way we can think about this first term here is that this is like a time-dependent amplitude. And the second term here describes the shape of the wave. So the shape of the wave, right, how it depends on space, isn't going to change with time. So the shape's always going to be the same. It's just the amplitude that's going to change with time. So to illustrate this, I have a little bit of an animated GIF again. So on the top we can see there's this red wave that's moving to the left, and below that I have a green wave that's moving towards the right. And then at the very bottom I have the sum of these two waves. And what we can see is when you have a wave that moves to the left and a wave that moves to the right and you add them together, we get this kind of wave that's always got the same shape. That's why it's called a standing wave. It's like it's standing still. We can also see that there are certain points here, like 3, 2, where the wave just kind of always seems to have the same point. The point doesn't seem to move up and down. And then there are other points in between this where the disturbance is very large. Now, because a standing wave is formed by a string with two fixed points, there are only certain wavelengths that are allowed. The wave that has the largest wavelength is called a first harmonic. And we can see by looking at this that the first harmonic has a wavelength that's equal to twice the length of the string, where this here is the length of the string. Okay, and you can see we have 1/2 of an oscillation in that space. Now the second harmonic has the second longest wavelength, and as we can see here we have exactly one oscillation over the length of the string. So the wavelength is equal to the length of the string. And of course we can have a third and fourth harmonic and so on and so forth. We can see here this third harmonic has 1.5 oscillations in this area, so the wavelength is equal to 2/3 the length of the string. Now I introduced just a bit of notation. It's very important. The node and antinode. So as I mentioned with the animated GIF that we saw before, there are certain points on the string where the wave doesn't actually move at all. Or I shouldn't say the wave, the medium, the particles in the medium don't actually get displaced at all. So these points right here are always at the same place. There are other points in the medium where the displacement is going to have a maximum. These are called antinodes. The fixed points are called nodes. So looking at this, we can see that there are 3 nodes here, 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 and here. Or 4 nodes, I'm sorry, and 3 antinodes. One here, and one here. So now let's go through and just do a simple example. The example says, a guitar has a string that's about 1 meter long, and both ends are fixed. When the third string on a guitar is plucked, it creates a sound with a frequency of 200 Hertz. So using this, what is the speed of the wave on this string? So I have my known values summarized up here. So remember that the speed of a wave is related to the frequency and the wavelength by this formula here. So all we need to do is figure out what the wavelength is. But I wasn't given that. But what I was given was the length of the string. So remember, I should have mentioned this in the previous slide. What we're talking about here is the first harmonic. Okay? So for the first harmonic, remember that's this kind of thing here. We have these fixed ends, and we have this kind of wave like this. Okay? So when you have this sort of thing, remember that the wavelength is equal to twice the length of the string. So plugging this formula into here, I see that the velocity is equal to 2 times the frequency times the length of the string. And now plugging all of my knowns into here, this value and this value, I can see that the speed of the wave must equal 400 meters per second. So I think I'll end the video there, and in the next video we'll start talking about what happens when a wave reaches what's called a free point or an open point. And this will also form standing waves that'll look just a little bit different, but the formulas that we get from it will be very similar.